It's time to get started with our 2D kinematics angle projectile notes. So we're going to start off our notes the exact same way that we started off our last ones, taking a look at the simulation below. So if we take a look at our simulation, we see that we have a cannon and it is being launched at an angle of 50 degrees with an initial velocity of 15 meters per second. Let's see what the cannonball's motion looks like when it's launched from the cannon. So we'll notice that we have that big green arrow that we talked about, and it's constantly changing direction, and it also looks like it's getting smaller and then bigger again. So let's take another look at this and let's slow it down this time. Initially, when we launch this cannonball out of the cannon, this big green arrow is just pointed at an angle. That angle is 50 degrees. And this big green arrow is indicating our initial velocity or our initial speed, which is 15 meters per second. As that cannonball goes higher and higher, we're going to notice that this arrow gets smaller and smaller, and the arrow also becomes more and more horizontal, which makes sense because when we're at the apex or the highest point right here, all of our velocity should be in the x direction, and that's why we see this arrow completely horizontally. And we don't see any y arrow. As we continue though, the y velocity arrow starts getting bigger and bigger, and now it points down. And the reason it points down is because gravity is accelerating it, speeding it up, and that's why it's getting bigger and bigger in the y direction. So let's take another look at it being launched, and we see that the y velocity arrow is pointed up, but as it goes up, it gets smaller and smaller and smaller. Then there isn't any at the apex, and then once we cross the apex, it gets bigger and bigger and bigger. The x velocity, you'll notice, stays the same the entire time. And we can see that right here, how it shows this horizontal arrow that continues to move horizontally and stays the same. Now let's take a look at the acceleration arrows, because we've seen these before. So I'm going to do total and component. If I launch this, I notice that there's only one acceleration arrow, and it's this big yellow arrow again. Hopefully you remember from the previous notes that big yellow arrow is just talking about gravity, because we know that when objects are in the air, the only reason they're accelerating is because of gravity, meaning gravity is the only force acting on this object while it's in the air. We also know that gravity points down, which is why this arrow points down. And lastly, we know that gravity is a fixed number on Earth, which should be negative 9.8 meters per second squared, which is why our arrow remains the same size the entire time. Something important to note is that if I increase this angle to 80 degrees, this projectile would be in the air longer than if I decrease the angle to a smaller degree. And I'll show that right now. So there's 80 degrees, and now I'm going to decrease it to like 25 degrees. Go ahead and fire it, and I'll notice that this cannonball is in the air for way less time. I can confirm that by taking my measuring tool here. At the 25 degree angle, it was only in the air for 1.29 seconds, and at the 80 degree angle, it was in the air for 3.01 seconds. The reason why it's in the air longer when we have a bigger angle is because it has a bigger maximum height. And we know that the time an object is in the air is just dependent on the height. Now that we've taken a look at the simulation, let's go ahead and talk about how we can solve these angled problems. So the first step is going to be similar to the 2D kinematic horizontal launch problems, in which we draw a diagram. We want to make sure that we include any numbers from that problem, and then we set the origin at our launch point. Next, we're going to go ahead and draw a triangle at that launch point, using the angle to help us solve for VOX and VOY, which we'll talk about in a sec. And then obviously it's a kinematic problem, so we need to list all of our variables in the x and the y direction. We should know at least 7 of these variables. Lastly, anything that we don't know, we're going to have to go ahead and solve for. So here's our first problem. As you can see, there's a lot of stuff going on here, so let's dive into it. So it says a ball is launched into the air at 9 meters per second from an angle of 42 degrees. So I'm going to go ahead and label my launch point, which we're going to say is right around here. And the angle, like it said, is 42 degrees. So I'm going to draw 42 degrees here. Next, I'm going to go ahead and draw where the x velocity would be, and that's right here, and label it Vx. Then I'm going to draw the y component of the velocity and label that Vy. Now that we've labeled our picture, let's go ahead and identify what parts of this problem are 0. Well, in order to do that, I need to draw my origin, which the origin is going to be where I'm launching it from. So right here is going to be my origin. So if our origin is at the launch point, that means that our initial distance in the x is going to be 0. For an angled launch problem, our initial and final distances in the y are the same, and they're both going to start and end at the origin, meaning that our initial and final distance in the y will always be 0 meters as well. Another thing that's 0 is the acceleration in the x, because we've said before that there's no forces acting on these objects in the x direction. The only force acting on an object in the air is going to be gravity, and we know that gravity points down, meaning that acceleration in the x direction, the horizontal, left and right, would be 0. Now let's talk about the acceleration in the y. Well, the acceleration in the y, like we just said, is gravity, because the y direction talks about the up and down, or the vertical. Therefore, gravity is negative 9.8, meaning acceleration in the y should be negative 9.8 meters per second squared. If we take a look, we can see that we have a lot of missing variables here. But some of them aren't really missing, they're just going to take a little bit of math to figure out. We don't need to use our equations, we need to use some trig to figure it out. So for Vox, we're going to figure it out by using a triangle. And Voy, we're also going to use a triangle to figure that out. So I've gone ahead and put a triangle on here for you guys, where it says our initial velocity, question mark. Well, in the problem it tells us our initial velocity is 9, so I'm going to label that 9. The angle in the problem, it also tells me that, which is 42, so I'm going to label that 42. Now down below, I have another triangle, and this is used to help me out and to figure out what type of trig function I need to use to figure out my missing sides. So if we take a look, since this is our angle here, the y is going to be our opposite side, and the x is going to be our adjacent side. So if we take a look at our triangle here, let's start by solving for the y. And since the y is the opposite side, I'm going to look down here and notice that I need to use sine. So I have sine of my angle, which is 42 degrees, is equal to the opposite, which is Vy, over my hypotenuse, which is 9. In order for me to solve for the velocity in the y direction, I need to multiply my 9 over. So I get 9 times sine of 42 is equal to Vy. Go ahead and solve, and I find out that Vy should be equal to 6.02 meters per second. So let's do something very similar for the x direction. The x is the adjacent, so I'm going to go ahead and use cosine. So I have cosine of 42, because it's the same angle, is equal to Vx over the hypotenuse, which is still 9. I end up with 9 times cosine of 42 is equal to Vx, meaning that my velocity in the x direction should be equal to 6.69 meters per second. So now that I have the variables that I solved for on the last slide, you'll notice that VO and VF in the x direction are the same again. And we said the reason for this is that acceleration is 0, meaning that we are moving at a constant velocity. Therefore, our velocity should be the same in the x direction. So let's go ahead and start by solving for our VF in the y direction. And to do that, we're going to look at which equation's only missing VF. We notice that we don't have T as well, so we can't use Big Dog, can't use Little Pup, we got to use Shaggy Cat again. Using Shaggy Cat, we get VF squared equals this. We notice though that VF squared is really just equal to VO squared, because 2 times negative 9.8 times 0 is just 0. Therefore, our final velocity in the y direction is negative 6.02 meters per second. Again, the reason why this is negative is because we are going down. And we know that a final velocity that points down should be negative. So go ahead and put that in my table down below, negative 6.02 meters per second. Now that we have almost all the variables in the y, we can go ahead and solve for time. Let's take the easy way out and use Little Pup. Using Little Pup, we plug in our variables and we find out that time for the y and x direction should be equal to 1.23 seconds. Now that we have time, we can go back over and solve for the final distance in the x direction. When solving for variables in the x direction, we can actually only use Big Dog, because Little Pup does not work and Shaggy Cat will not work for the x direction when an object is in the air. Therefore, if we use Big Dog, we end up with dfx is equal to 0, because that's our initial distance, plus VO, which was 6.69, times t, which is 1.23, plus 0. The reason it's plus 0 is because it's at squared, which we know a is 0, so all of that just turns to 0. Multiply through, we find out that dfx should be equal to 8.23 meters. And again, dfx is just saying the final horizontal distance. All right, we've made it to the end again. Let's go ahead and talk about some helpful tips and tricks. The object will always land at the same height it was shot from. Therefore, our DOY and our DFY are always going to be 0. Other things that are always 0 is going to be our initial distance in the x and acceleration in the x. We know that acceleration in the y is always negative 9.8 meters per second squared. And again, this is just because of gravity, and gravity only acts in the y direction. VFY is always negative because we're falling down. If we want to solve for Vy with a angled launch problem, we need to use our trig function, which if we simplify it is really just our total velocity times sine of theta. Doing the same thing for the x, we get our total velocity times cosine theta. So these are just simplified equations that I recommend you guys write down somewhere and use as kind of a shortcut. If we're ever asked to solve for the final angle, that's going to be equal to inverse tangent of Vy over Vx. It's important that when you solve for Vy over Vx, if Vy is positive, you put positive, and if it's negative, you put negative. You can have negative angles here. A negative angle just means that you're going into the ground. Lastly, the time in the air is only going to depend on the initial launch angle. As the initial launch angle increases, your velocity in the y direction is going to increase as well, meaning that the time in the air is going to increase. But our velocity in the x direction decreases. Vice versa, as the initial launch angle decreases, velocity in the y direction decreases, and the time also decreases, meaning that the velocity in the x direction increases. Here's the two pictures that we saw before, where on the left side we have a big launch angle. We can see that we reach a higher maximum height, and on the right side we have a smaller launch angle, meaning that we reach a lower maximum height.